Hi everyone, it's Mr. Wells again, and this video I want to look at a classic type of physics problem. This is called Atwood's machine. So in Atwood's machine you have a frictionless pulley, a massless pulley, um, and two blocks hanging over it of different masses. And so if you think about it, what's going to happen when the system is released, we hold them steady, the blocks steady, and then we release them. So if M2 is greater than M1, then what's going to happen? M2 is going to drop down, M1 goes up, okay? So M2 accelerates down, and M1 accelerates upward. Okay, so we're going to use the same strategies that we've used in all these problems. So we define this. So the state of motion of the system is going to be acceleration. And then, of course, we want to draw free body diagrams for each block. So for M1, we're going to have a tension force T1 going up, and we'll have a weight force equal to M1 times little g going down. And for block 2, we'll have a weight force equal to M2 times little g and a tension force T2. Okay. Now, before we start writing equations, let's think about the constraints here. So these two things don't just move freely in any direction. So M2 and M1 are both going to be accelerating. We also know that because we have a massless rope and a massless pulley and all that kind of stuff, on the two ends of the string, the two T's are actually the same. So T1 is equal to T2, which we'll just start calling T. So I'm actually just going to, I'll just erase here if you don't mind my doing that. So I'm going to erase T1 and erase T2. So the two tension force on each end of the string is going to be the same. We also know that these two things are going to have the same magnitude of acceleration. So, so in terms of magnitude, A1 is equal to A2. So we can say that, if the acceleration of block 2 down is 4 meters per second squared, block 1, since it's attached by a string, and the string is not going to change length, that it has to have that same acceleration upward. So I'm going to call that A. Okay. And then there's sort of one other, I hate to use the word trick, but there's one other thing that we need to look at in this system. So usually we define up and down, like an upward acceleration would be positive and a downward acceleration would be negative. In this case, the two things are going to be, one's going to accelerate upward, one downward, but they're really the same magnitude. So anytime you have a pulley in a situation like this, that's going to help us define this. So I know that this rotation, this pulley is going to rotate that way. And so I'm going to call that basically positive. We're going to let that define positive. So what that means is for M2, positive acceleration would move the pulley clockwise like that. So positive A is going to be downward. And for M1, positive acceleration will be upward. So that's going to help us set these equations up properly. And so that's not something you necessarily would think of yourself. Okay, so when I set up these equations, so I want to set up my force equations. Okay, and so the sum of the forces for M1, okay, since up is positive for this one, I'm going to write this as T minus M1 G. And for 2, I have down is positive. So when I write the sum of the forces, that's going to equal M2G minus T. Okay. And there should be a subscript 1 there on that one. Now for each of these, we can then set up Newton's second law. I know that the sum of the forces has to equal the mass times the acceleration of the object. So I've got T minus M1G is equal to the mass of that object, M1 times its acceleration. So that's Newton's second law, F net over here on the left side, MA on the right side. Same thing over here, only this time we are going to have M2G minus T is equal to M2A. Same thing, we're setting up Newton's second law for that. So now I have two equations, and if we look at the knowns and unknowns, our tension is unknown. Our M1 is usually given, little g we know, M2 is usually given, and so we really have two unknowns, the tension and the acceleration. So knowing the masses of the objects, I have two equations and two unknowns, and so we could solve for the tension and the acceleration of the masses and the tension in the string. So I will leave that as an exercise to you when you get to do a problem. Okay, so this is the special case called Atwood's machine, and this business with the positive accelerations is the thing that you probably need to know about. You can also consider you're going to run into some problems in your book and other places where you end up with a pulley and an inclined plane. So if you have something like this, so we have an inclined plane with a pulley on the end, and we're going to have some sort of block here, and we'll have a string going around and some sort of block over here, so that one of these things is going to be in motion. It depends on the masses and the angle and all that stuff about whether the block in the incline is going to slide down the plane or up the plane. But it's the same kind of situation. You do the same sort of thing. So if, for example, the block is sliding down the plane, if it's sliding down the plane, then we could have A in that direction. Then the pulley would be like this. So you could consider that the positive direction. So if I were doing my free body diagram for this block over here, I would have T and mg, and since this direction is positive when I write the sum of the forces, that's going to equal T minus mg. So T is going to be in the positive direction. So that's really all you need to know about Atwood's machine. From there, if you go back to our previous slide, from there you are going to look at what you're given and so on and solve for the tension or the acceleration. All right, so I hope that helps. Thanks for your time.